What in the world? Break out your notebooks, boys. We're going back to school.
You can see the riding on the pavement. Young kids, they're growing up in basements.
This is going to be the first of a multi-part series that I'm titling 383 Basics. And the purpose of this series is to go into some detail on the different aspects that are involved in building a 383 stroker small block Chevy. The first episode is going to be on compression ratio, which is not 383 specific. It applies to just about every single combustion engine out there, but it is the foundation of a lot of the principles and things that we're going to talk about in upcoming episodes on this. So I want to get into compression ratio. We're going to focus on static compression ratio. That's the compression ratio that most people talk about whenever you hear anybody using the term compression ratio. There is dynamic compression as well, but we're not going to be focusing on that in this episode. So what is compression ratio? What compression ratio is, in a nutshell, is the volume that you have in your combustion chamber whenever the piston is at the bottom compared to the volume that you have whenever the piston is at top dead center. And there's a few components that you're going to need to know to get that information, and I'll go into some detail on what those are. So the different things that you're going to have to know to find your compression ratio are going to be your bore, your stroke, the combustion chamber and your cylinder head, whether the pistons have a dish or a dome and how much that is, so basically the cc's of your piston that you're using, your piston to deck clearance, your head gasket thickness, and the number of cylinders. So there's a lot of calculators you can find online, which is what I would recommend doing, but you are going to need to know the information of each one of these points to input in that calculator to get the compression ratio, or at least theoretical compression ratio that your engine will be running. So the first thing to discuss is going to be bore. And what is bore? Bore is the diameter of the hole or the cylinder in which the piston travels up and down inside. And on a small block Chevy 350, the standard bore on that is going to be 4 inches. Now for a 383, it could be a combination of a few different things, but a standard 383 would be a 30 thousandths over bore, which would bring that to 4.03. That's pretty sloppy 3. A little hard writing sideways. 4.03. So there are different combinations. You could do a 40 over, which would be 4.04, or you can even do up to a 4.06 is typically as large as you would want to go to bore out the cylinder wall on a small block Chevy. But it is done technically. Going anything larger than a 4.03 or 30 thousandths over is going to be larger than a 383. And actually in my application, I'm probably going to be looking at doing a 40 thousandths over bore, which depending on a few different variables, which I don't want to get ahead of myself on, but it could technically be 384, 385, so on and so forth. It really depends on what combination you have. But even if you have a 40 thousandths over bore, you would typically just still consider this a 383. So it's going to apply across the board. It really is just the situation that you run across. Since our engine is already 30 thousandths over bore, we're probably going to be looking in that direction to go 40 thousandths, but that's a conversation for another time. So the next variable that we need to discuss is going to be stroke. And what is stroke? Stroke is the distance in which the piston travels from its uppermost point, which is called top dead center, to the lowest point in the cylinder. The distance that travels there from the top to the bottom is the stroke. And the way that the stroke is either added to or reduced is all done in the crankshaft, which I have one here in front of me. So this is a crankshaft. The distance in which these rod journals are offset from the center, which is called the main journals, determines how much of a stroke the piston has inside the cylinder. Now if you think about it, the farther that this rod is from the main journal, the offset there, it's going to determine how far down it goes and how far up it goes. If you increase that distance, it's going to push the piston down lower in the cylinder on the bottom stroke, and it's going to bring the piston and rod up higher on the top dead center stroke, or otherwise known as the highest point in the cylinder. So what I just showed you there was a stock 350 Chevy crankshaft, which has a stroke of 3.48. So with the 383 stroker, what you do is you bump that stroke up to a 3.75. So by increasing the stroke or the distance that that piston travels up and down, what you're doing is adding more volume inside the cylinder and reducing it whenever you're at top dead center. So what that does is it accomplishes being able to take more air and fuel on the intake stroke, and then you compress that down tighter. So it's the volume on this is getting greater, and then you're squeezing it even tighter than you otherwise would at factory levels. The ability to have more volume in your chamber and then compress it even tighter at your top dead center stroke on your combustion allows for you to have a lot more power. You're taking all that energy and cramming it down tighter, all that air and fuel that you have in your cylinder, and then that way whenever the spark ignites it, it provides a lot more energy on your combustion stroke. So a 383 stroker, especially the longer the stroke that you have, gives you more torque. So 383 strokers are very torquey, which gives you very good response on the street, a lot of low end power. That torque is what you feel in your seat whenever you hit the accelerator and you take off. So now that we found our stroke, which is 3.75 for a 383 stroker, the next few things are going to have the most to do with changing your compression ratio for a 383 stroker, because like we had discussed previously, the first two things, your bore and your stroke, are going to be pretty common on a 383 stroker. They're not really going to change. The bore is the thing that's going to be most common to change, which will, make your compression ratio. If you keep everything else the same, it will change it because it's a larger area that you're compressing, like we just discussed with the volume. But for the sake of the conversation, we'll call it a 4.03. We'll say that these variables are going to stay pretty consistent. They can change, but they won't as much as these other things will. So the next thing is combustion chamber. And what the combustion chamber, we kind of touched on it a little bit. We said the combustion chamber is where that air and fuel is compressed. But whenever we discuss combustion chamber as far as getting our compression ratio, what we want to know is how much area we have in the combustion chamber on our cylinder head. And I have a cylinder head here with me. I'll kind of show you what exactly I'm talking about. So if you look at the cylinder head, the pocket that you have in here where the valves are, the larger this chamber is, the more volume you're going to have in your top dead center. And the more area you have at your compressed state, the lower your compression ratio is going to be. Because if you remember, we want to have a lot of area at the bottom of the stroke, and then we want to try to squeeze that down as tight as we can, which is going to be at the top dead center. So the smaller that you have this area at the top, the more power you're going to make, the higher your compression ratio is going to be. But that's all within limits, which I'll get into a little bit farther down in this video. But that's going to be accomplished with your cylinder head. Depending on how big your chamber is really going to affect a lot. So whenever you're building a 383 stroker, you need to, or really any engine this applies to, you need to know what your target compression ratio is whenever you're getting parts. Because if you just throw stuff together, it might run, it might not. So I just want to pause and talk to you about detonation. So like we discussed, the more compression you have, the more power you make. But that's within parameters. There's a limit to that. Whenever your compression is too high for the fuel that you're running, you'll run into something called detonation. What detonation is the pre-ignition of your air-fuel mixture before its intended point, and it does it explosively. That is explosive. It does it very violently and abruptly, and whenever that happens, it rocks your piston, your rings, your connecting rods, your bearings, all your valves, all the components of your engine take a beating. And whenever you have that beating, if it persists for a long period of time, it will cause mechanical failure in your components. You crack a piston, you could break a connecting rod, destroy your bearings, tool up a valve, all sorts of things, you name it. So it is important to know what your compression ratio is when you're building it. That's honestly probably the biggest point of this whole thing. Too low of a compression, your engine won't run properly or at all if it's low enough. And too high of a compression ratio, you'll run into detonation, which will cause mechanical failure, and then it won't run either. So for a pump gas, you're typically, if you're running 93 octane, you can run on cast iron heads. You could run about 10.5, 10.6 to 1. And with aluminum heads, they dissipate the heat a little bit better, so you can run a little bit higher, up to about 11 to 1. But that is the max that you want to go. And again, depending on what application that you're running and you're intending the vehicle to be used at, really determines. You don't always want to go, bigger is better when it comes to compression ratio. It's all about the intended use of that vehicle. And just to talk about the fuel, the octane rating, you see like 85, 87, 91, 93, whatever you have at your gas station, the octane isn't really the power or whatever in it that a lot of people think. The octane level is how much you can compress that fuel before it ignites and how long it takes to burn. So those two factors weigh very heavily on detonation and compression ratio. For race applications, you can use race fuel. Race fuel has a much higher octane in many cases, and you could run much higher compression ratio because of that. It's 13s, 14s, whatever you want to, you're looking at that point. But for pump gas vehicles, for aluminum heads, the standard is to limit it at 11 to 1. With cast iron heads, you pretty much want to limit that at 10.5 to 1 or 10.6 to 1. And that's about as far as you want to really push that. For the application of my truck, the 72C10 that we're working on, my goal is to aim for that 10.4 to 10.6 range, because I don't intend this vehicle to be a daily driver. It's going to kind of be a weekend cruiser, have fun with it, kind of tear it up on the street a little bit. Legally, it's important, but whatever. So I'm going to aim for that range for my application. So different chambers that you're going to want to run. I mean, you could run a larger chamber and then accommodate for that difference with some of the other things we'll talk about. But let's just say, for the sake of this discussion, we'll call it a 64cc chamber. So your combustion chamber for your cylinder heads is going to be measured in cc's, cubic centimeters. As is the next thing that we're going to talk about, which is going to be pistons and dish or dome or flat tops. And I'll explain the difference between those three things. And they are also going to be measured in cc's as well, cubic centimeters. So essentially what you have for a dome or a dish or a flat top, what you see right here would be a flat top. The piston has no recesses or domes to it, no dish or dome to it. For a domed piston, you can see there's all different kinds. But a domed piston would have a raised point, which again, what that would do is at your highest point at top dead center, if you reduce the area in there, the volume in there, that is going to increase the compression ratio because you're squeezing that tighter. Conversely to that, if you have a dish, your piston is going to have a little bit more area in it, and you're going to, depending on how much of recess in your piston you have, you're going to decrease the compression ratio because you're increasing the volume at the top dead center at your combustion. So with me, I have a piston, and if you could see, it has a little bit of a dish. So these are dished pistons. You have your top point, and then they run down a little bit. And you also have something that's called a valve relief. You have little angled notches, and what that is it's clearance for your valves. Whenever your valves come down at top dead center, you need to worry about piston to valve clearance, which we're not going to get into that in this video. But especially if you have a dome and you have a really tight chamber, and depending on how much lift you have in your cam, you're going to have valve reliefs or clearance for that valve to come down so it doesn't make contact with the top of the piston. So I raced a 64cc because I don't want to get anybody confused on if they're trying to build a 3-to-3 stroker. You don't need a 64cc cylinder head or combustion chamber on your cylinder head to build a 3-to-3. Again, whatever variations you do is going to change your compression ratio, and my recommendation is whenever you gather this information, Summit Racing has a really good compression ratio calculator, so you go on their website and look it up on Google, and many other people have them as well. You can kind of play around with different variables, like some other things that we have to discuss yet, like your piston dish or dome, or flat tops, which would be 0, or your cylinder head combustion chamber. All those things are different variables that are going to fluctuate a lot, and depending on your application and the parts you have. So regardless, I erase that to not confuse anybody. So as far as dish or dome though, whenever you're sourcing your pistons, your rotating assembly, whatever you're planning on doing, some manufacturers do not call the spec a dish, which can be confusing. Sometimes they call it a negative dome. So you'll see it on displayed like this, which is the same thing. A negative dome, although confusing, is the same thing as a dish, because essentially it's a dome inverted. So if you see negative dome, if you're looking for dish pistons, that's what that means. So don't be too confused on that. Flat tops are called flat tops, domes are called domes. So the next variable that we need to discuss, piston to deck clearance, my favorite. I found this to be the most frustrating part when trying to source parts, especially for something that's not stock, other than stock, for a 3-to-3 stroker, which everything about a 3-to-3 stroker, I'm sorry, is not stock. And there's a lot of different things, which is why I'm putting together the series. So hopefully I could give it to you guys in small bites, some of the things that I've learned and frustrations I've gone through, and kind of walk you through and explain the different parts of it. So hopefully if you're doing this, it will kind of give you some insight and maybe answer some questions or frustrations that you two are having or might have in the future as you do your own build. So piston to deck clearance, what is that? Piston to deck clearance is how far the piston, the top of the piston, is from the deck, which is the flat part, the top of your engine block, how far that piston is from the top at top dead center. So if you don't have, and this has been the biggest frustration for me trying to find things, if you don't have an assembled short block, essentially, so the bottom end of your engine in front of you that you can measure it and have the parts that you plan on buying already installed, you really don't know what that distance is going to be. So oftentimes you're going to have between a 0, a flush, or no piston to deck clearance in your cylinder chamber. So that means that the piston is going to be the same height as your deck, or you're going to be probably typically as much as 15 thousandths, 0.015 down. So that's called, if it's down, it's called in the hole, and if it's up, it's called out of the hole, which does happen. You can factor that in. Obviously that's going to affect your compression ratio, because that is going to add or subtract from the volume at the compressed, which we talked about here. If you're down from your cylinder here, it's going to increase or decrease your compression ratio but increase the volume, and then opposite to that, if it's higher up or flush, you're gonna have a tighter area in there. So, how do you find that? How do you find piston to deck clearance? Well, if you have everything assembled, you can take a bridge with a micrometer. A bridge basically is a device that goes across or bridges across your cylinder, and then you have a micrometer. It's basically a dial that has a little spring in there that will tell you how far or how above something is. To measure, what you would do is you would zero it out at the top of the deck, so that gives you your 0 point. You bring your piston to top dead center, which is all the way up, and then you'll slide your bridge with your dial caliper over to the center of the piston. You want to make sure it's in the center so you don't get an inaccurate reading in case the piston might be a little offset from one end to the other. So that's going to give you your most accurate point is in the center. And then how far down or how far up that dial goes is going to read out on a dial caliper and tell you how far in or out of the hole your piston is to give you your piston to deck clearance. So you don't really have that information at your disposal if you're going to be sourcing parts and you don't have everything assembled, especially in my case. Like I said, I've got my cylinder heads already, so that's going to be a fixed variable that I need to kind of control the different parts and pieces that I have for my build. The only thing that I've came up with is you could measure your deck height, and your deck height is essentially it's going to be the center point of your crankshaft to the top of your deck, which is going to be this distance here. That is your deck height. And again, this isn't really a fixed variable when you're talking about small block Chevys, especially a factory one. If you have, say, like a blueprint block or something of that nature, an aftermarket one, you're going to have a much tighter casting. There's going to be a tighter tolerance in it, so you might have that information. Typically on a small block Chevy, a stock one, you're going to have a deck height of 9.025. And again, there is going to be variation in that with the stock block. If you have an aftermarket like a Blueprint or a Dart or something similar, like I've said previously, you'll have a tighter tolerance on that and you might have that information. You can measure it. The way that you measure it, like I was saying earlier, is you measure from the center line of the crank to the top of the block, and that will give you whatever that actual thing is. But just for a loose, safe measurement, you can use 9.025. But to get that for sure, you do want to measure that. But if you have that number, let's just say for discussion's sake, it's 9.025, you can add up the length of all of your rotating assembly and you can subtract it from this number, and that will tell you the distance that you have from the deck to the piston, or piston to deck clearance. So what you want to do is you want to do half your stroke plus your connecting rod length plus your piston compression height, which brings us to our next thing that we need to know: piston compression height. What is piston compression height? Piston compression height is the distance from the center of your wrist pin to the top of the piston. So looking at this actual piston I have in front of me, this is going to be your wrist pin. So you'd measure the center line of this wrist pin to this top surface of the piston. And that's your piston compression height, the measurement that you have there. That's everything that's above the connecting rod. The reason why you wouldn't measure the whole thing, obviously you've got the different part of the skirt or different lengths, and the connecting rod doesn't stop at the bottom of any of that. So your measurement is going to be from there, because whenever you measure your connecting rod, your measurement is from the center to the center. So this is going to be the center to the top of the piston. So as I have it measured or written out here, connecting rod length is really from the center to the center of the connecting rod. And again, we'll get more into connecting rods and the different lengths that you have or can use in 383 stroker. We'll do that probably in the next episode, I think. But for now, just talking about compression ratio, that's your piston compression height, and that gives you your additional length. So whenever you add that up, that's essentially going to be the distance from the center, the distance of the connecting rod, and then from the top of the connecting rod or center of the connecting rod to the top of the piston, that's your whole length there. And so if you subtract whatever this measurement is from this, that will tell you how far in or out of the hole it is. If it's a negative, obviously that's going to mean you're out of the hole. If it's zero, it means you have zero clearance. And if it's a larger number greater than zero, that's going to be in the hole. So that's a way that I have been able to kind of figure out what that's going to be. But again, it brings us to another problem that I've been having, especially with part suppliers, and this isn't just one or two, this is a lot. Most piston manufacturers, or especially when you're looking at a rotating assembly specifically, they don't tell you what the piston compression height is. I'm sure you could probably call the manufacturer, but whenever you're looking at a rotating assembly and one that might have parts from different manufacturers, it can be really frustrating trying to figure that out. Again, if you have your parts in hand, you can measure, so it doesn't have to be assembled. But again, if you have your parts in your hand, you're better off than someone like how the position that I'm in right now is I don't have my new pistons, my new connecting rods, my new whatever, crankshaft, etc., which is all part of your rotating assembly. I don't have that on hand right now, so I can't measure that. I don't know what pistons I'm going to have, and I can't order a piston until I know what it is. So, I was able to, so far with what I'm looking at, kind of figure a lot of these things out. And again, not to really throw you guys off and confuse you further, which I probably am on a pretty good trend of, but there's also taller compression height pistons that people make, different manufacturers, to accomplish having a tighter clearance to raise your compression ratio. It's called your squish or your quench in there, without having to cut the deck. Cutting the deck is milling down the surface of the block to bring that down. So there's a few different ways that you can accomplish essentially the same end goal of adjusting the squish or the quench, or your compression ratio, etc. So I don't want to go too far on that. I probably already went a little tick over into kind of getting a little bit confusing. But the meat and potatoes of all that is, if you have everything in front of you, if you have your short block and your rotating assembly installed, use a bridge, use a dial caliper, and you're good. Okay, that's how you get that. If you don't have that information and you can find the lengths, obviously you're gonna know your stroke, you're gonna know your connecting rod length. That's readily available. Finding your piston compression height might be a little frustrating. You call the manufacturer and I'm sure they can give it to you, and then you can just kind of play around with that, and then you can add that up, subtract it from your number, and that's your piston to deck clearance. Yeah, so that's the next part. The second to last thing, which is really, your number of cylinders, we can kind of jump ahead on that. That's pretty in your face. In this case, it's a V8, you got 8 cylinders. That's not going to change, or at least you sure hope it doesn't change. So you have head gasket thickness. Again, you have a head gasket. I've got one here. This is an old one that I took off of the block whenever I took it apart. And although it's something very paper thin, it plays into your compression ratio a decent bit actually, because this is going to space out your cylinder head from your block or your deck height or whatever you want to call it, the top of your cylinder. So it's going to add or decrease the chamber volume. And whenever you're factoring this in, you want to use the compressed thickness. So that's how thick this gasket is whenever it's fully tightened down, because as you tighten it down, it's going to squeeze tighter. So it's important to use that number whenever you're doing that. There are also, again, not to go too far on a tangent here, but another factor that does have another role in playing into compression ratio is how big the bore on your gasket is, because your bore size on your gasket is going to be a little bit bigger than the bore on your actual cylinder, because obviously you don't want it to be in the cylinder chamber, so you want it to be a little bit bigger. But again, if you go a little bit bigger, even though it's a small, minute amount of volume, you are adding to that volume. Or if you do a little bit tighter, you're reducing it. So definitely something that you need to take into consideration. Most calculators, like the Summit Racing one that I referred you to earlier in this video, doesn't require the gasket bore. It does call for the compressed gasket thickness though. So there's all different kinds. And again, if you kind of have an idea, or if you have some of your parts like I do, and you're making things work or need to make it work for your target compression ratio, you can kind of plug and play a few different sizes of head gaskets. You can find that any auto parts store, any speed parts store, Summit Racing, Jags, whatever, you name it. And they will give you all of those numbers as far as compressed gasket thickness and bore and whatnot on the website whenever you look it up. And it's local not hardware, but auto parts stores will have all these too. It's not something that needs to go through like a speed parts place like Summit Racing or Jags or one of the others. So whenever you get that information in, you add all that up, and that's going to be, plug that into a calculator, and that's going to give you your compression ratio. So it's very important to have all this, have a target compression ratio, figure out what kind of driving you're going to do with the vehicle. If it's going to be a drag race vehicle, if it's going to be kind of like a hot rodder on the street, like the 72 C10 is going to be, my 383 stroker, where you want to have a high compression ratio, but still want to be able to fill it up at a gas station on pump gas. And it's also not going to be something I'm going to be daily driving, because the higher compression ratio, you're also going to want to run at a higher RPM. Otherwise, you can run into detonation issues, like we already discussed. Is a big problem. You don't want to have it. That's no good. So hopefully this all helped you. This is going to be the first of many videos that we'll kind of go into. I believe the next one's probably going to be into connecting rod length and the differences between them, and applications in which you'd want to use one over the other. And then we'll kind of go from there on some of the other things, such as other clearances and et cetera, as we go on farther in the build and the series. Hopefully this helped you. Hopefully it wasn't too much. And thank you guys all who stuck around and listened to me flap my gums. Get outside, get working on your project. It seems complicated, but it's really not. Whenever you get these numbers that you need and plug it in the calculator, it's really no big deal. And most of them are provided. The only one that I'd say is a little tricky is piston to deck clearance. And that's only if you don't have the parts in front of you or assembled. So get outside, get wrenching on something, piss off your neighbor, disappoint your mom, and until next time, keep on keeping on.
You can see the